Hello students, hope all of you are well. So today I welcome all of you in my third video lecture about the Taylor series and the Laurent series. So in complex analysis, often we are using these two series to describe the structure of the analytic function in different domain. It can be simply connected domain, it can be multiply connected domain. So how we are going to explore this kind of series expansion. Not only that, these two series are having huge impact on the complex analysis. Later we are going to discuss about the singularities of an analytic function, residue, poles, etc. So there these two series are playing the huge role, so that we are going to explore also. So in this lecture I have planned to cover the following topics, that is the Taylor series expansion along with the problems, thereafter the Maclaurin series, next Laurent series, and some practice question from all the series, that is the Taylor series along with the Maclaurin series and Laurent series. So the first series that today we are going to start, that is about the Taylor series. So what is a Taylor series? Suppose we are having an analytic function f of z within a circle C. So that is the first most important part which I am highlighting here. So we are having one analytic function which is analytic within a circle C, and the circle is centered at a point z equals to z0. Then for each point z inside the circle, the function f of z can be expressed in the form of an infinite series. What is the expansion? F of z equals to f of z0 plus z minus z0 into f dash of z0, that is the first order derivative of zf. Thereafter we are putting the value of z0, z minus z0 whole square divided by 2 factorial into f double dash of z0. So it is quite similar to the Taylor series that we have learned in the real analysis, right? So now this expansion, this is the expanded form of the Taylor series, which we can write down in the form of an infinite series structure in the closed form, that is summation n equals to 0 to infinity an z minus z0 whole to the power n, that is in the form of a power series, because here we can see that is an is coming is in the power, right? Z minus z0 whole to the power n. And what is an? An are the coefficients which can be taken from this, right? So that is f to the power n z0 divided by n factorial. Now let me just tell you how the idea is coming. So for Taylor series, always remember we should have the analytic function within a circle C. So for your understanding, I have already drawn the axis here, real axis and imaginary axis. Suppose we are having a circle here. The center of the circle is z equal to z0. Okay. Now within this circle, at each and every point, the function is analytic. The function f of z is analytic at each and every point of this circle. So if we consider the circle is of radius r, so basically we can write down this circle as mod of z minus z0, that is equals to r, that is the perimeter of the circle. Now if we want to get the whole region of the circle, then we have to write down it as mod of z minus z0, that is less than equal to r. So which not only include the boundary, which also includes the interior points of the circle. So for this type of region, always we have to create the Taylor series, okay, for some inequality will come in the region. Now let us come back to the discussion. So as you know that we have discussed already in the previous video lecture. If you have not visit it, so please visit it and make your concept more clear. So in the last video lecture I have taught about the Cauchy's integral formula along with the problems, so please visit the video lecture. Now we know that for the Cauchy's integral theorem, if we are having an analytic function over some region, and in the region one point is an interior point, then we can find out the nth order derivative of the function, that is f to the power n z0, by using the Cauchy's integral formula n factorial by 2 pi I integration over c f of z by z minus z0 whole to the power n minus 1 dz. So this thing already we have learned in the Cauchy's integral formula. So here you can see for Taylor series f of z, we have written it as a n z minus z0 whole to the power n, where a n is the coefficient of this power series, which is nothing but f to the power n z0 by n factorial. Now how we will find out this f to the power n z0? Using the Cauchy's integral formula, because it is satisfying the condition of the Cauchy's integral formula. Z equal to z0 is the interior point of the circular region. Okay, so a n equal to f to the power n z0 by n factorial, which can be written as, this n factorial can be cancelled out whenever we'll put the value of f to the power n z0 from the Cauchy's integral formula. So the coefficient value of a n for this Taylor series can be easily obtained using this formula, 1 upon 2 pi I integration over c f of z by z minus z0 whole to the power n plus 1 dz. Okay, though we have to not have to use these things in our syllabus, we are having simple problems, straightforward questions which can be easily solved. Don't have to calculate those kind of a n, but if you are having some critical functions where the coefficients are not coming very easily, for those things we have to apply this formula for a n. Now we come to one special case for the Taylor series. Suppose particularly if we think that z0 is nothing but the particular point 0, that is the origin itself. So what will be the diagram for this case? So if this is our imaginary axis and this is our real axis, so we want to plot one circular region which is centered at a point z equal to z0. Okay, that is the origin. So inside this region, along with on the boundary of the circle, the function is fully analytic. If it happens, then Taylor series takes the following form. So in the above Taylor series formula, simply we have to put z0 equals to 0. So f of z becomes f of 0 plus z into f dash of 0, z square by 2 factorial f double dash of 0, z cube by 3 factorial f triple dash of 0, and so on. It is not a finite series, it is going up to infinity. So it can be written in the closed form also, and the closed form that you can see, that is a n equals to 0 to infinity a n z to the power n, where a n is nothing but f to the power n 0 by n factorial. Just like the previous one, we have substituted the value of z0. So in Taylor series, whenever we put z0 equals to 0, this series is known as the Maclaurin's series. So what is the difference between Taylor series and Maclaurin series? Whenever the circular region is considered only centered at the point origin, so it is a special case. And if we choose any other point except z0 equals to 0, suppose z0 equal to 1, z0 equal to 2, 3, 4, any other point x apart from 0, that will be general Taylor series expansion. But for particular case, we are having z0 equals to 0, then we will get the Maclaurin series. Now let us come to the next important series, most important for exam, and also you will get many questions in the end semester exam also from the Laurent series. So you have to understand it very carefully. So for Laurent series, what is the statement that let us try to understand. Suppose we are having C1 and C2 be two concentric circles. Concentric circle mean that both of they are having the common center. with respective radius are r1 and r2 with r1 greater than r2. So let us try to draw the region first as per the given information. So we are having the real axis as well as the imaginary axis here. Now we have to draw two concentric circles. Say we are drawing here. Say this is the first circle and this is the another circle. Say both of they are being taken with center z equal to z0. Okay, so this circle which is the innermost circle, so interior circle is having the name C2 with the radius R2 from here, and the outer circle is having the radius R1 which is named as C1. So if we are having two concentric circles, so everyone can see that one region is inscribed in between these two circles, right? That is in the shape of a annular region, right? It is a shape of a ring type of region is there. That is nothing but the annular region. So for Laurent series, it says that suppose we are having this type of annular region and one function f of z is taken in this annular region, where this function becomes an analytic function within this annular region D. Now if it happens, then for each point z inside this annular region, so if we choose any arbitrary point inside this annular region, say this is a point z equal to z1, this is another point z equal to z2. So if we choose any different point in this annular region, the function f of z can be expressed as a form of addition of two series. It is not like a Taylor series. For Taylor series we are having only one series where the power series, the terms are coming in the positive power only, right? So here we are having two series summation n equals to 0 to infinity a n z minus z0 whole to the power n. Another series, it starts from n equal to 1, not n equal to 0. Why? Because it is a power, negative power. So if we take n equal to 0, it will become undefined. So it is becoming bn z minus z0 whole to the power minus n. So we are having two integrals. First is I1, second one is I2. How we can get these coefficient values? This is also coming from the concept of the Cauchy's theorem. So an equals to 1 upon 2 pi I, that I have already discussed just now before this one, that 1 by 2 pi I integration over c fz by z minus z0 whole to the power n plus 1 dz. And for bn we are having 1 by 2 pi I integration over c fz z minus z0 whole to the power minus n plus 1 dz. So where the first integral part, that is this part, is known as the regular part of the integration, which will contain only the positive power, because here n is a positive integer, so it will start from 0, so it will create the positive powers only. Okay, and here the first power should be 0, that is non-negative power also we can say, not only positive power, it can be written as the non-negative power. And for the second part, this is very important. In the next video lecture we are going to explore many things depending on the second part of this series, which will contain the negative powers only, bn z minus z0 whole to the power minus n. So this part is known as the principal part of the Laurent series. Okay, so this negative part is known as the principal part of this Laurent series. So what is the difference between Taylor series and Laurent series? For Taylor series we are having one simple circle. Within the circle the function is analytic. For Laurent series we are having one annular region, that is two concentric circles are there. In between one region is there where the function is fully analytic. Okay, so for this kind of case we are having addition of two series where the first series is basically coming from the structure of the Taylor series and along with one negative power series. First part is the regular part, second part is the principal part of the Laurent series. Now let us come to some useful formulas that we are needed for the next solutions. So these are basically the infinite GP series. All of you know these formulas, so please keep it in your mind and please note it down if you want to do some problems. Okay, there is 1 plus x to the power minus 1. This is the expansion, 1 minus x plus x square minus x cube and so on. The region of the convergence is mod x less than 1. Whenever modulus of x is less than 1, then only this infinite series is going to converge. Similarly, I have written this rest of the expansion along with the condition for the convergence. Now we will come to the solution problems. So let us come to the first question. There is a easy question. So here we have to find out the Taylor series expansion of the function f of z equals to log of 1 plus z, right? Log of 1 plus z, and about which point it is given, about z0 equal to 0. So basically you can imagine it is not only a Taylor series, a special case of Taylor series, which is nothing but the Maclaurin series, right? So now how to find out the Taylor series? So before we start this problem, we have to draw the region, okay, for region of this Taylor series. So here it is the real axis, here it is the imaginary axis, and now the series we have to draw which is having the center at a point z0 equal to 0, right? Now one circle will be there over which we have to find out the Taylor series. In this question, one extra part has been given, that is the interesting part. Find the region of convergence. Okay, that is, we are having the circle, we should have the circle inside which the function should be analytic and we can find out the Taylor series. That is okay, but what should be the region of convergence? That means what should be the radius of this circle? It should not be it go to up to infinity. So up to which limit we can consider this region? We will discuss at the end of this problem. So before that we will start to find out the Taylor series. So it is a mechanical problem, simple problem it is. So fz equals to log of 1 plus z. To find out that normal Taylor series, we need the derivative of this function. First order derivative, second order derivative, third order derivative. So first order derivative of log of 1 plus z is 1 upon 1 plus z. Double derivative is minus 1 upon 1 plus z square. Triple derivative 2 by 1 plus z whole cube. Simply we are substituting this point z0 equals to 0 at each and every step. Okay, so f of 0 is log of 1, that is equals to 0. F dash of 0, that is 1 by 1 plus 0, so it is equals to 1. F double dash of 0 minus 1 by 1 whole square, that is a minus 1 only. F triple dash of 0, that is equal to 2. So we are making some derivatives and we are substituting the value z0 equals to 0 here. Now we will put all these values that we have obtained here in the final expression of the Taylor series. So f of z is what? F of 0 plus z into f dash of 0, z square by 2 factorial f double dash of 0, and so on. So in each and every point there is f0 equals to 0 itself. F dash of 0 is 1, so 1 into z. F double dash of 0 equals to minus 1, so minus 1 by z square. F triple dash of 0 equal to 2. 2 divided by 3 factorial. 3 factorial is 6, so 2 and 6 it will cut down and we will have z cube by 3. So this is our required answer. So in your exam, if such kind of question will come, you have to bring the answer up to this, z minus z square by 2 plus z cube by 3 and so on. Now let us come to the interesting part, that which will be the region of convergence. Okay, so now let us look at the function. So here the function is log of 1 plus z, right? So log of 1 plus z, we know that this function will be undefined if z value is less than or equal to -1, because if we put z equal to -1, it will become log of 0, which is undefined. Along with that, if we put some negative value more than -1, that is basically less, that is -2, -3, -4, etc., then we will have inside of log minus number, which is also not defined. So we cannot go -1 onwards, right now. So if we cannot go -1 onwards, now what will be the structure of the circle? So circle center at a point z equal to 0. Here it is -1. So to make a circle, we have to take uniform radius, that is +1. Here we cannot go beyond +1, and we cannot go -1 and onwards this side, right? And also we cannot be able to touch -1. So before -1 we have to stop. Before -1, if we have to stop, then what should be the region of convergence? Then the region of convergence will be just before -1 and before +1. So inside this circle, the function will have its Taylor series expansion. But we cannot touch +1, we cannot touch -1. So here also I have written less equal to, it is not correct. Let us make it correction here. So it should be particularly mod z. It should be mod z strictly less than 1. It should be mod z strictly less than 1. Okay. Now let us come to the second question. This type of question also you will face in the exam, either the first type or the second type. Okay, so the question is, we have to expand the function f of z equals to z plus 1 by z minus 3 z minus 4 in form of a Taylor series about the point z equal to 2. Also find the region of convergence. Same type of question, but here what is the difference between the previous question and this question? For previous question, one known function has been given to us, and it is quite easy to do the derivative and substitute the point. But here the function is given in the form of a rational function, right now, something pz by qz. So if we want to make the derivative will going to be huge, because it is u upon v. So we have to apply every time u by v rule. Complex derivatives will come, and we will not be able to find out 2-3 terms after. It will be calculation error also can be there. So for this type of question, how we will approach towards the problem? If it is given that about z equal to 2, we have to find out the Taylor series, we have to substitute something in place of z equal to 2. So what should we substitute? We will do this type of thing, that is, since the Taylor series is about z equal to 2, so each and every terms of the Taylor series will come in the power of z minus 2. We take 2 on the left hand side, so it will come z minus 2, right? Everything is going to come in the power of z minus 2. So what we will do, we will put some substitution, that is u equals to z minus 2. So what is the value of z? Z is going to be u plus 2. So now in function f of z, what is given here? F of z, that is z plus 1 divided by z minus 3 z minus 4. We have to substitute z equal to u plus 2. So function will take this form, u plus 3 divided by u minus 1 into u minus 2. Now we have to make the simple partial fraction. Partial fraction I think all of you know, so I don't have to explain it. So since these are two linear factors, we have a upon u minus 1, b upon u minus 2, and we have to substitute and find out the value of a and b. So for simple calculation, we are getting a equal to -4 and b equal to 5. So what is the value of f of z we are obtaining? That is -4 upon u minus 1 plus 5 by u minus 2. So now we have taken -1 common, so we are having 1 minus u whole inverse. Why we have taken this -1 common? What is the reason behind it? Because that just before this solved problems, I have shown you some useful formulas we are having, right? That is 1 plus x to the power minus 1, 1 minus x to the power minus 1. So those infinite geometric progression series expansion we have to apply at each and every problem wherever it is useful. So we have to make the structure like 1 minus x to the power minus 1. So we have taken 1 minus u to the power minus 1. And how it can be taken? That is 2 I have taken outside along with this minus sign. So 5 by 2 is outside. So inside what will come? 1 divided by 1 minus u by 2. So this can be written as 1 minus u by 2 whole to the power minus 1. Right. So now we just apply the series expansion. So 1 plus u square u cube, like so on. Similarly, minus 5 by 2, 1 plus u by 2, u by 2 whole square, u by 2 whole cube, and so on. Now just open the bracket and just collect the coefficient of this is 4 minus 5 by 2, 4 minus 5 by 4, like this I have collected and just simplified. So after simplification, we don't want the result in terms of u. U we have substituted by ourselves, right? So we have to substitute the value of u at the last. So what is the value of u? We have u equals to z minus 2. So everywhere we have to substitute this is z minus 2. So this is our final answer. That is the Taylor series coming in terms of z minus 2. How you will be able to understand that your calculation is correct? If you look at this structure, you will be able to see that every term is coming in the power of z minus 2, whole square, whole cube, and so on. So that is one way that you will be able to understand that you are doing some correct calculation. Now let us come to find out the region of convergence. So as per the given question, the function is given as f of z equals to z plus 1 divided by z minus 3 z minus 4, right? Z minus 3 z minus 4. So if it is z minus 3 z minus 4, if I put z equal to 3 or z equal to 4, then the function will become undefined. So it will become not analytic. So we cannot put the value z equal to 3, we cannot put the value z equal to 4. But as it is the need of Taylor series, we need a circle, and we have expanded the Taylor series about z equal to 2. So our center is given, that is z equal to 2 is given to us, but we cannot put z equal to 3, we cannot put z equal to 4. So what should be the region of convergence now? Let us try to understand. So here it is suppose 0, here it is 1, here it is 2, here it is 3, here it is 4. So we have to make a circle which will be center at a point 2, but we cannot touch 3. Before 3 we have to stop. So what will be the circle? Just before 3 we have to stop. In this region the function should be analytic. Okay, so that is the Taylor series expansion, and this is the region. So what is this region? That is mod of z, it is given z minus 2, right? So mod of z minus 2 is less than 1, because the radius is what? 2 to 1 to 2, distance is 1, right? This distance is 1. So we have taken this region, mod of z minus 2 less than 1. So in this region the Taylor series can be exist. Similar problem I have given here. You just go through it. Same type of question. That is the Taylor series expansion of the function f of z 1 upon z minus 1 z minus 3 about the point z equal to 4. So same thing, that is, since if we are having any rational function and the point is given as z equal to 2, 3, etc., then we have to put or substitute something. So here we have substituted u equal to z minus 4. So z equal to u plus 4. Like the previous question we have done, same process we have to repeat. And finally, after doing the partial fraction, getting the values of the coefficient a as well as b. We have to substitute in the function, and we have to write down the series expansion formula that we have received previously, that is 1 plus x whole inverse 1 minus x whole inverse. That structure we have to bring and write down the series expansion. Okay, and finally, don't just leave the question by keeping u with u, just you substitute the in place of u the value of in terms of z, that is u equal to z minus 4. And the region of convergence for this question is also mod of z minus 4 is less than 1. Now let us come to some problems of the Laurent series. Okay, this is very important and vital, and from here also we are going to get some difficult type of scenarios in the complex plane. So first of all, we are having one function 1 upon z minus 1 z minus 2. We have to find out the Laurent series expansion for the region. First region is mod z less than 1. It is a circle. Inside the circle, second region is 1 less than mod z less than 2. Third region is mod z greater than 2. Fourth region 0 less than modulus of z minus 1 less than 1. In the exam also you will get the question similar to this. Same type of 2-3 regions will be given, over which you have to find the Laurent series expansion. So 1 upon z minus 1 z minus 2, what is will be your first task? You have to first find out the that is the partial fraction. Okay, so we are having two linear factors here, so a upon z minus 1 plus b upon z minus 2. So we have just cross multiplied it, a1 equal to a into z minus 2 plus b into z minus 1. Now substituting z equal to 1, we get the value a equal to minus 1. Substituting z equal to 2, we get the value b equal to plus 1. Right, now after getting all the values of a and b, after getting the values of a and b, what we are having here, that is 1 by z minus 1 z minus 2 equal to minus 1 upon z minus 1 plus 1 upon z minus 2. Now the important part is going to come for the question. For first part, it is given as modulus of z is less than 1. Okay, very good. So let us try to imagine. So we are having modulus of z less than 1. So modulus of z less than 1 means it is a circle, center at a point 0. How we are getting the center? Because z minus z0, so z0 is 0 here and radius is 1. So we are having the circle like this, right? It is not touching 1, equality is not there. So here it will just before 1 we have stopped, and here also just before minus 1 the circle ends. So in this region the function is analytic, and within this region we have to expand. So since two factors are there, z minus 1 and z minus 2, how we are going to decide? This is the very important part. Please listen it carefully. So for the case of z less than 1, if we say modulus of z less than 1, so if I divide the left hand side by 2, that value will be more or less, right? Suppose we write down 1 by 2 is less than 1. So if I divide 1 by 2 by 2, then it will come 1 by 4. That will be definitely less than 1. So if modulus of z is less than 1, then modulus of z by 2 is also less than 1. So why we have taken this? Let us try to understand. So f of z equal to minus of 1 by z minus 1 plus 1 by z minus 2. We are having two separate factors. So from this one I have to take minus sign common to get 1 minus z whole inverse structure. But from this one I have to take 1 by 2 common, so that z by 2 will come and z by 2 is less than 1. It will satisfy the condition. So 1 by 2 I have taken common. So it is coming 1 minus z by 2 whole inverse. Now it is usual, the expansion form, that is 1 plus z square plus so on, 1 plus z by 2 plus z square by 4 and so on. So what I have did, z less than 1, so for this 1 I have taken common, mod of z by 2 less than 1 I have taken common 2. We are having this. Now let us come to the second case, second scenario, that is 1 less than mod z less than 2. So for this one also let us draw one region. So this is our real axis, this is our imaginary axis, but here what is the structure they are saying? Mod z is greater than 1. Okay, very good. So this is our mod z equal to 1. Now they want mod z greater than 1, so we have to go outside of this 1. But mod z is less than 2 also. Very good. So we are having mod z less than 2 also. So this is the annular region, right? This is the annular region over which we can see that we have to find out the expansion of the Laurent series. So here it is 2, here it is 1. So 1 less than modulus of z less than 2. So if we are thinking for this part, 1 less than mod z, it imply what? 1 by z will be less than 1. Modulus of 1 by z will be less than 1. Why we are doing all these things is less than 1 concept? Because we want to apply the geometric progression series structure, that is 1 plus x whole inverse formula, 1 minus x whole inverse formula. For all those formulas you have seen that I have written the region of convergence is mod of x less than 1. So to apply those formula I have to make all these common dividers, that is the common difference by less than 1. Similarly we are having mod of z less than 2. So how we can make it less than 1? Divided by 2 itself. So modulus of z by 2 is less than 1. Okay, now for f of z is what? Minus of z minus 1 plus 1 by z minus 2. Now see this carefully. So what we have to do, since we have taken written 1 by z is less than 1, we have written here that is 1 by z is less than 1. So from the first term we have to take common z, okay, from denominator. So it will come 1 by z, this structure, this is 1 by z. And from here 1 by z minus 2 we have to bring z by 2. How to get this z by 2 form? We have to take 2 common, so it will come z by 2. Okay, so now the rest of the part is easy. 1 minus 1 by z whole inverse, this is, we are applying the same geometric progression series formula. 1 minus z by 2 whole inverse, this one. So here we are having some interesting thing. It is actually coming as the Laurent series structure. How? So basically this part, if you look here, all the z are coming in the denominator, so it is the negative power of z. So this is the principal part. This is the principal part, and here all the terms are coming positive, so it is the regular part. So it is the full Laurent series expansion. Now we come to the next part, that is modulus of z is greater than 2. Very interesting thing. So how to get? Let us draw the diagram again. So here we are having the real axis, here we are having the imaginary axis. So modulus of z is greater than 2. So here two circles are there. First circle, the radius is 1. The second circle radius is 2. Just before this question we have done the second part. Now it says that modulus of z is greater than 2. So the region is lies where? The region is outside, right? This is the region, outside the region. So again we have to make using mod of z greater than 2 to less than 1 concept. So how to get that one? So if mod of z is greater than 2, 2 divided by mod z should be less than 1. How I have done? Just I have divided by mod z on both sides. Now you see, if mod z 2 by z is less than 1, that is already you are in this region. So if this region is outside 2, so this region is outside 1 also, this circle also, inner circle also. Therefore 1 by z will be also less than 1. Right now, why? Again I am explaining, because this region that I am shading here, this region lies outside the outer circle. So for this region we are having mod z greater than 2, which is similar to 2 by mod z less than 1. So this shaded region, if it is outside the outer circle, then this is outer of the inner circle also, right? Because inner circle is small na, compared to mod z less than 2. So that is 1 by z less than 1. So here f of z is minus of 1 by z minus 1 plus 1 by z minus 2. Now what we have to do, if we have to make this 2 by z and 1 by z structure, from first factor we have to take common 1 by z. From the second factor also we have to take common 1 by z. So the structure will come, that is 2 by z along with 1 by z. Now the series expansion is usual. So that is the formula for the Laurent series. Let us come to the next one, that is 0 less than mod of z minus 1 less than 1. How to do this? Since it is given in another form, here the center of the circle has been shifted to 1. For the previous all the questions we are doing the center of the circle about 0 only. So for this question the center of the circle has been shifted. So this is our real axis, this is our imaginary axis. Now the circle is centered at a point 1 and it cannot go beyond 0 and less than, so z minus 1, right? And it is less than 1. So radius of the circle should be less than 1. So the circle will be like this, shifted. So for this shifting, what we have to do, we have to also do some modification. So for previous type of question we are just substituting u equal to z minus 1. So whenever this type of problem will be given, you have to consider some different substitution, either t equal to z minus 1 or u equal to z minus 1, what you wish to do. So z equals to u plus 1. Now again we have to substitute all those values in terms of u. So f of z is coming minus 1 by u plus 1 by u minus 1. So whenever we have converted from this z minus 1 to u, so what we are getting, 0 less than mod of z minus 1 less than 1, it becomes 0 less than mod of u less than 1. Okay, so if mod of u is less than 1, then what we have to do, simply we have to take common 1. There is no division is required, already it is in the form of mod of u is less than 1. So from this one, that is minus 1 by u, we don't have to change anything for this part. For this part we have to just take minus sign common, so that 1 minus u whole inverse it will come, and we can apply the normal series expansion for 1 minus u whole to the power minus 1. After getting this, we have to substitute all the points, that is u in terms of z, that is u equal to z minus 1. So this is the Laurent series expansion. Let us come to the next question of the Laurent series expansion. That is very interesting. The interesting part is about the partial fraction here. While most of the student made the mistake for this kind of partial fraction, here the structure of the function is given as z square minus 1 divided by z plus 2 into z plus 3. So if you look at this structure, numerator the highest power of z is 2, denominator also, if we just open the bracket, we will get the highest power of z is 2. For all the previous question, the denominator, in the denominator the power of z is at least more 1 greater than the power of z in the numerator. But here both numerator and denominator are containing same power of z. So if we are having how to do such a partial fraction, So to do this partial fraction, we have to write down the partial fraction in this manner. That is 1 plus a upon z plus 2 plus b by z plus 3. Why this 1 is coming? Because to adjust the power, that equal power, z square minus 1 is there. So to adjust the equal power, we have to add 1 plus. Now rest of the problem will be as it is. Okay, so after doing this partial fraction, we will get the value of a equal to 3, b equal to minus 8. Now let us come to the first part, that is for mod z less than 2. So if it is less than 2, we have to make it less than 1. How to do it? Divided by 2. So mod of z by 2 is less than 1. So mod of z by 2 less than 1, very good. But we are having another factor here, z plus 3. So if mod of z by 2 is less than 1, so mod of z by 3 will be also less than 1. Because if we are dividing anything by 2 and its value is coming less than 1, so if you divide it by 3, it will become more small. So it will be definitely less than 1. So for this structure, f of z equal to 1 plus 3 by 2. That is from the first factor we have to take common 2, so that this z by 2 structure is coming here. And from the second factor we have to take common 3, so that this z by 3 structure will come here. Okay, now we have to just write down the reciprocal form, 1 plus z by 2 whole inverse, 1 plus z by 3 whole inverse, and write down the series expansion, that is 1 plus x whole inverse, 1 plus x whole inverse. Okay, now we come to the second part, second question, and that is 2 less than modulus of z less than 3. 2 less than modulus of z. So if 2 less than modulus of z, we have to make it less than 1. How to do it? Divided both sides by z. So 2 upon z is less than 1. But mod z is less than 3. So mod z less than 3, how to make it less than 1? That is z by 3 is less than 1 divided by 3. So for the two factors, the two terms we are having, what to do? From the first, since z plus 2 is there, so from here I have to make this 2 by z concept. 2 by z, how to get? By taking z common. So if I take z common, inside it will come 2 upon z. And how to get this z by 3 concept? To take 3 common. So if I take 3 common from the second term, we are having z by 3. Now usual series expansion, 1 plus x whole inverse, 1 plus x whole inverse we have to apply. Similarly, we are having the third one, that is modulus of z is greater than 3. So modulus of z is greater than 3. How to make it less than 1? Divided by z. So 3 upon z is coming less than 1. So since we are having two factors, so 3 upon z, if it is less than 1, definitely 2 upon z is less than 1. The concept that I have already told for the previous question. Now we are having two factors here, 3 by z plus 2 and 8 by z plus 3. So how to get this 3 by z? To get this 3 by z, we have to take common z. Then the 3 by z terms will come here. How to get this 2 by z? We have to take common z, so that we will get 2 by z here. So basically you have to understand, depending on the region choice, which term you have to take common. Either you have to take common the constant, or you have to take common the z itself. Now how to understand it? Let me just give you one hint to remember this concept. It will be helpful. So suppose we are having the real axis along with the imaginary axis. Let me draw the circle centered at 0, because everything we are doing mod z less than 1, this type of thing. So we are having the first circle, say like this. Now we are having the second circle, which is the concentric circle. We are assuming the center is at 0. Not necessary that every problem we have to center 0. For the previous question also, the last part you have seen that center has been shifted. Now what to do? Whenever it will be given the first region, about the first region. So for this first region, you have to take constant common. So that the structure will form mod of z less than 1. This type of structure will come. If we are having this annular shape of region, if we are having this annular shape of region, then depending on the choice, what we have to do, we have to take z common as well as constant common. So that the structure will come mod z less than 1. And if it is going beyond this region, this outer, then for outer region we have to take, for both cases, for inner circle, for outer circle, for both cases we have to take z common only. We have to take z common only, so that the structure will come mod z less than 1. This type of structure will come. Okay, so now I have given many questions, solved questions here for your practice. So this is the last question. It is quite similar to the previous one, only the difference is in place of 2 factors, here in the denominator we are having the 3 factor, and here it is given 1 minus mod of z plus 1 less than 3. I think you can be easily be able to understand this problem also, since this type of thing is given mod of z plus 1 less than 3. So for this type of case we have to do the substitution. So u equal to z plus 1, z equal to u minus 1. First of all we have substituted this. In terms of u, everything is coming. We have to do the partial fraction. After getting the partial fraction, as per the region, since already given it is in the annular region, 1 less than mod of z plus 1 less than 3, that is 1 less than mod of u less than 3. So from there we have to take common u as well as 3, that I have told you just now, that we have to take common z as well as constant. So one constant I have taken common for the outer circle, and for the inner circle we have taken common the variable. Okay, and we have written the Laurent series expansion in this manner. So this is the final result. Please go through it, try to practice by yourself, and then side by side you just see my video, so that the calculations error, whatever you will have, you will face the difficulty, you will be able to understand. Okay, so with this today's session I am ending now. So if you understood all these concepts, please like, share and subscribe the channel.